Newton's law of gravitation states that the force between two bodies is proportional to the product of their masses and is inversely proportional to their separation squared. When answering this question, that needs to be written as I spoke it and not as I wrote it. In part B, it asks us to consider the centripetal force on a planet in a circular orbit around a sun. Okay. So first of all, we take the force between the planet and the sun, which is G times mass of the sun, mass of the planet over their separation squared, and that must be equal to the centripetal force on the planet. Straight away we can cancel out the mass of the planet and one of our r's. So we end up with an expression with v squared on one side is equal to gm over r. We also need to consider that v is equal to omega r, and omega is 2 pi over t. So we can write v squared as being equal to 4 pi squared over t squared r squared. Now if we substitute this back in here for v squared, we end up with 4 pi squared r squared over t squared is equal to g m over r. Now if I cross multiply by t squared and cross multiply by r and divide by gm, I end up with an expression t squared is equal to 4 pi squared r cubed divided by gm, and therefore I can say that t squared is proportional to r cubed, which is what the question asked us to show. When questions of this type come up, we just use what we derived previously, t squared is proportional to r cubed, and plug in the numbers that we're given. So we're going to work in days, and our answer will come out in days. So 365 squared is some constant times 1.5 times 10 to the 11 cubed. If we work that out, we get our constant being 3.947 times 10 to the minus 29. We then put our constant back into the formula, but working with the radius of Mercury to find out what the time period of Mercury is. So t squared is our constant, this time times the radius of Mercury's orbit cubed, and that comes out as t squared is equal to 7,662, which gives the time period of Mercury's orbit as 87.5 days. In part 2, it's asking us to calculate the ratio, the distance from the Sun to Neptune. This is just the radius of Neptune's orbit over the distance from the Sun to the Earth, which is the radius of Earth's orbit. So we're going to use our same formula again. I'm going to work it out over on the right hand side here. This time we can say that t squared over r cubed is a constant. Okay, exactly the same as what we did in part 1. But t squared over r cubed for the time period of Earth and the radius of Earth must be equal to t squared over r cubed for those values for Neptune. So I can say time period of the Earth squared over the radius of the Earth cubed must be equal to the time period of Neptune squared divided by the radius of Neptune's orbit cubed. If I rearrange this, I get the radius of Neptune cubed over the radius of Earth cubed is equal to the time period of Neptune squared over the time period of Earth squared. Now we know the time period of Neptune. This is 165 Earth years, so 165 squared. We're working in years this time, so the time period of Earth in years is just 1, which gives us 27,225. This is the ratio of the radius of Neptune to Earth's orbits cubed. So if we take the cube root of this number, it gives us the radius of Neptune divided by the radius of the Earth is 30.